All right, hello everyone. So problem 10, determine the work input during the compression of steam from 10 kilopascals to 1 megapascal in an adiabatic pump operating at steady state and an adiabatic compressor operating at steady state. So we're given a compressor and a pump for case A and B, or pump and a compressor, I should say. And the only difference here, you're still compressing water from P1 to P2, but the only difference is that you are compressing liquid in the pump and then you are compressing gas in the compressor. So what's coming into the pump at state 1 is a saturated liquid. What's going into the compressor at state 1 in the compressor is a saturated vapor. So we need to find the work for each, and each of these has an isentropic efficiency, and I guess I should probably put that on there, but an isentropic efficiency of 85%. So 0.85 over here. Oops, and that's not a pump, that's a compressor. The pump has an isentropic efficiency of 85%. All right, so first things first, the typical assumptions that we make for both devices are that, let's see, Q dot's equal to 0, and then changes in kinetic and potential energy are equal to 0. Of course, both of these are operating at steady state, but that's given to us. And that's it. So for each of these, for the pump and the compressor, we have, if we applied our first law, so I'm looking just at the pump really, but it's our first law is still going to boil down for the pump and the compressor to be the same thing. Our first law is going to give us, we've got dE dt equals ... And we've done this plenty enough times so that I know that what I'm going to end up getting, try to color coordinate the best that I can, I'm going to get that W dot is equal to m dot times h1 minus h2. And so, of course, I want to get little w, so of course this is going to be little w, which is equal to that w dot divided by the m dot, and that's going to be h1 minus h2. So for my pump, that's what I'm looking at right now for state 1, my h1, got a quality of 1 and we've got the pressure. So this is going to be got H at P1, quality of 0. And we can look this guy up in table A, what is this? A3. So this is an A3, and we'll get that we have, actually, let's go ahead and go there right now, might as well. So if I look in table A3, so we are at 1 megapascal, I'm sorry, not 1 megapascal, 100 kilopascals, no, yeah, 100 kilopascals with 1 bar. So right here, and my quality is 0, so it's like there's my H sub F value, 417.46. So let's go ahead and write that on our sheet here. So 417.46, and that's kilojoules per kilogram. Go ahead and erase that. Now state 2, I'm sort of at a loss because I have the pressure, but remember, in order to fix the state, we need 2 independent intensive properties, right? Temperature, pressure, specific volume, quality, if it's applicable, internal energy, enthalpy, and entropy. And I'm not given anything except for pressure. But I am given some information about the isentropic efficiency. And remember that isentropic efficiency is going to relate the ideally isentropic process, which I know how to describe that, right? Isentropic, delta S is equal to 0. and the actual process, which is what I'm trying to describe, right? This is the actual work. So the isentropic efficiency of that pump, ideally, wouldn't have to put a lot of work into that pump. So he's in the numerator, and this is going to be H1 minus H2S. And then actually, I'm going to leave this little W as he is because isn't that what I'm looking for? Right? That's convenient. That is what I am looking for. He's right there. So if I calculate H2S, I've done my work, right? That's all I need. So here I go. So H2S, this is, of course, my pressure is 1 megapascal. So 1 megapascal, or what, 10 bar? Yeah, think about it for a second. So 10 bar, but my entropy, S2S, is the same as S1. So maybe I kind of go back up here and I'll put it beside that guy. So this is still at P1 with a quality of 0, right? Quality at state 1 is 0. And so I can go ahead and get that guy. So this is 1.3026. So 0.026, and this is in kilojoules per kilogram K. Perfect. So then this S2S is 1.3026 kilojoules per kilogram K. All right, and so now I need to fix my state. Now, I can actually tell you exactly what state it's going to be in before I look in, and that's before I look in those tables, and that is because if I sort of think about on a TS diagram, so going into that pump, I was going in as that water was going in, not me personally, but the water is going in as a saturated liquid, and so it's going to be right on that saturated liquid line. The pressure is going to increase and the temperature is going to increase too, not that much, but it is going to increase. And if we're talking about an isentropic process, the entropy is not going to change, and so it's going to go straight up. Obviously, I have exaggerated the amount that it's going to go up, but that's the point. It's going into that compressed region. So you can verify this as well. So let's do that. So if I go to my tables, table A3, 10 bar. Let me get this guy out of the way. So if I look at 10 bar, I can see that my entropy, which was 1.3026, is less than that S sub F value. So I'm clearly in that compressed region. And so I've got a couple of choices here. Well, I've got one good choice actually, now that I think about it. Let's look. So table. But there we are. No. There we are. All right. So I'm in, no, I'm sorry, that's A4. Need A5, compressed liquid. So let's see if I do have, uh-oh. So my pressure, P2, this is 1 megapascal or 10 bar, and you can see in my compressed liquid tables, the lowest pressure that we go to is 25 bar. And so I could extrapolate here, but I don't really want to because, right, extrapolation, you're going to get, if you're interpolating between two values, it's going to be a little bit better than if you're extrapolating. But, you know, I'll put that as an option. So could extrapolate. In table A5, those are the compressed liquid tables. But I could also use that equation for reversible steady flow work for a pump. So remember, for a pump, got this expression, the integral VdP, and this is really for any steady flow reversible work, but it's really convenient for a pump because that specific volume is constant. We assume that's constant, and I guess that really should go in there. So for my pump, maybe I'll say that specific volume is approximately constant. And so if I do that, if I say that it's constant because I'm saying it's incompressible, the specific volume comes out of the integral, then all I have is the integral dP, which is just P2 minus P1. So it's negative V times P2 minus P1, which is V times P1 minus P2. So just to sort of recap, this, and this are all the exact same quantities. Okay. Now, I will say, if you do extrapolate for H2S, you will end up getting a slightly different number than what we're going to calculate with the VDP. And that's okay. That VDP is also, you're going to have a little bit of error with that. You're probably going to have more error with that if you extrapolate. But either method of solving for my purposes on a test, either method of solving for WS is going to be just fine. So, but I like the VDP equation. So, hey, so great. Let's go ahead and get V1. Since we're already saying V1 and V2 are the same, let's go ahead and get that. So it's state 1, quality is 1, or quality is 0, and we're at 1 bar. So let's go back to table A. There we go. All right, so it looks like that's our quality right there. Of course, we've already multiplied by 1,000, so it's not 1.0432, it's 0.0010432. So let's make sure that we write that down correctly. So this is 0.001 0432, I think. Now I'm relying on my memory. Okay, so perfect. And so now I think I'm good. So this is what I'm looking for. So I think what I'll do is I'll just rearrange this and get an expression for that work. So it's going to be VDP minus P2 divided by that isentropic efficiency of 0.5. You're going to have to watch your units here. So this is 0.0010432 meters cubed per kilogram. And then your P1 minus P2. So I'll give you a hint. If you're in SI units, if you put your pressures in kilopascals, the units are going to work out right here, but I'm going to show you why. So you have 1,000 kilopascals, 1 megapascal, 1,000 kilopascals minus 100 kilopascals. Now I think I need to zoom in here, probably. Yeah. So got 1 kilopascal is a kilonewton per meter squared. And a kilonewton meter is a kilojoule. And so let's make sure that I should end up with kilojoules per kilogram. So let's just make sure. So I've got, that becomes meters cubed, cancels out with that one. The kilopascals cancel out, kilonewtons cancel out. That should be correct. All right, and so I should be left with a work input. Should get, I've got negative 1.105, and this is in kilojoules per kilogram. And this is the work required for that pump. box that guy. All right. For part B, of course, I need to find it for the compressor. So I'm going to do the same thing, apply my first law, right? So the only difference is instead of going in as a saturated liquid at 100 kilopascals, I'm going in as a saturated vapor. So let's go ahead and get that guy. So if I apply my first law, it's over here. My first law, it's still going to give me that little w, and I'm talking about the compressor work, but that little w is going to be H1 minus H2. Right. So, yeah. And here I've still got the problem of, well, I don't know enough information about state 2. The only intensive property that I'm given is that pressure, and of course I need something else to tell me about state 2. And so here's where I'm going to use my isentropic efficiency again. So the isentropic efficiency of my compressor, it's the ratio of the two works. Ideally, I wouldn't have to put a lot of work into it, so that's going to be the number on the bottom. And then, of course, that, I guess, is what I'm looking for, isn't it? Oops. That's what I need. That is what I need. Right. So I'll actually leave this as it is. I'm going to highlight that because that's what I'm looking for. Oops. And this is going to be not H1 minus H2, but H1 minus H2S. And I'll just put a little square for H1. It's going in as a saturated vapor, so we've got the pressure 1 megapascal, oops, and we've got a quality of 1. So this is going to be H sub G at 1 bar. So let's go look at that. So not looking at these subscript F anymore, but we're looking at, and I think I need, and I'll lose track. There we go. So I need a H sub G value. So that's this one right here. So 2675.5. 2675.5. And this is kilojoules per kilogram. And then H2, well, we know the pressure, and this is H2S, not H2. We know the pressure, that's 1 megapascal or 10 bar. And then because we're describing an ideally isentropic process, this is going to be S2S, which is equal to S1. So I probably do need to get S1. In fact, I'm going to scooch this down just so I can kind of keep the, oh, fine, I'll just rewrite it. I'm going to move that down because I kind of like to keep the properties for state 1 together. But this is going to be S at P1 and a quality of 1 at state 1. It's going to be the S sub G value, 7.3594. Gamma. So 7.3594. And this is kilojoules per kilogram. And actually K, I'm sorry, that off. And H2S is equal to H at P2 of 10 bar and an S2S that's equal to S1. And just like I kind of looked at that TS diagram for the pump, I could do a similar thing over here. This is not necessary, and you can definitely figure out what phase you're in just by those two properties, right? But you can also reason out what makes sense. So if you think about it on a TS diagram, state 1 went in as a saturated vapor. If you're compressing it, the pressure's going up, the temperature's going up, And if it's isentropic, then clearly it's going to be going into that superheated region. So that's state 2s, that's 1. And actually, now that I am thinking about it, this should have written this as 2s. Yeah. So, but you can verify that it's superheated. So let's go look in our superheated tables and figure out what that corresponding H value is. So superheated tables, here we go. So we are looking, there we go. Nope, not there. I got excited for a second. So we are looking at 10 bar, perfect. So here we are in table A4. We know the S value. The S value, the entropy was 7.3594. So it looks like if this is my entropy and this is my enthalpy, so 7.54, and whatever this corresponding H2S is, that's our H2S. So let's see what I've got. Let's see, 3194. That looks good. 3194.9. So I'm going to put that on my sheet here. So 3194.9, and this is kilojoules per. Perfect. And so now I've got enough information to calculate what that work is. And I end up getting negative 611 kilojoules per kilogram. And what you'll notice is that the work, it's a pretty big difference, right? You look at the work required for the, oh, I'm sorry, and this is not pump, this is a compressor. If you look at the work required to compress a liquid or to compress a working fluid between P1 and P2, so those are the pressures that you're looking at, it's much better to compress it as a liquid because it's going to take you less work to do so, right? You're still compressing. In this case, you were compressing water from 100 kilopascals to 1 megapascal, and the only difference was that with the pump, you're doing it as a liquid. With the compressor, you're doing it as a gas. So if you, as an engineer, if you have the choice, you want it to be as a liquid, right? Because it's going to take you less work. Okay, so let's see what we can do with this problem. All right, so problem 11. This is a steam turbine, and it looks a little bit ugly because we have two outlets, and I believe we might have worked one problem in Unit 3 where you had a turbine with two stages. But essentially what's happening is you've got, let's just look at case A. So case A is where you have the pump operates isentropically. So this is isentropic. And then on the right-hand side for case B, you have an isentropic efficiency of 88%. So, but what's happening just by sheer fact that it's a turbine, you have all the mass flow coming in at state 1, and it passes over this series of rotating and stationary blades, and some of it comes out here, right? That's m.2, and the rest of it passes through and is fully expanded and comes out at state 3. And the way that the problem is phrased, they say that 10% of the steam is extracted at the end of the first stage. So the way that we say that is that's 10% of the mass is extracted at the first stage, and then the remaining 90% is allowed to fully expand. Okay, so perfect. All right, so we want to know the power output for each of these cases. So I'm going to go ahead and I'm going to apply my first law. I'm also going to apply my first law. So I'm going to look at case A. So my first law, I'll write out the whole thing, because typically, you know, when we've had turbines in the past, it's been one stage, but it's not that bad. So we have H, I'm going to ignore the kinetic and potential energy changes, so I'll leave those as it is. It's inlet, outlet. Okay. So for a turbine, for any turbine, regardless of whether it has multiple stages or not, we're going to say that Q dot's equal to 0. Great. Uh, we're going to say that changes in kinetic and potential energy are equal to 0, right? Unless otherwise specified. And I'm looking at this at the problem statement. The reason that we know that case A is isentropic is because it's both adiabatic and reversible. So those are the words that tell you that it is isentropic. All right, but let's go ahead. Oops. Let's ignore kinetic energy changes and potential energy changes. It's steady state. It's adiabatic. And so this is going to be sum of the m dot h's coming in minus the sum of the m dot h's going out. And so you just have to be methodical. So going in, you have things going in at once. So this is m dot 1, h1. And then you've got two exits. So m dot 2, h2, m dot 3, h3. And the way that the problem statement is worded is it says it defines m dot 2 and m dot 3 really in terms of m dot 1. So what I'm going to do is I'm going to isolate m dot 1 on the outside. So it would be h1 minus 0.1 h2, I'm sorry, minus 0.9 h3. Right? I haven't changed anything. I'm just putting things in terms of how we defined this guy and this guy. All right. So, and I've got m dot 1. I just need to get all of those h values. So this really isn't too terrible. But this is where my h1, we look back up here, I've got pressure and I've got temperature, and that is enough to fix my state. So 6 megapascals or 60 bar. It does end up being superheated, so I will go to the superheated tables at 60 bar, 500 degrees Celsius. Let's see what I've got. Kind of in the right area. So table A4. There we go. Perfect. So 60 bar. Is it again 600, 500, 500. So all along this line right here. So 3422.2 is our enthalpy. For 20. And this is kilojoules per kilogram. Perfect. Now I'm going to go ahead and pull out the entropy value because I have a feeling that since this thing operates isentropically, that's going to be something I'm going to be interested in. So my entropy value is 6.8803. 6.8803. And that's kilojoules per kilogram K. Perfect. All right. So state 2. So it's expanded all the way from state 1 to state 2. So that process from 1 to 2 is an isentropic process. And so H2, and that's going to be, it really is, it's H2S, H3S, right? Because it's isentropic process. So H2S is going to be the enthalpy at P2, which is 1.2 megapascals or 12 bar. And an S2S that's equal to S1. So let's figure out what phase we're in. So you can look in your, by the way, just highlight. So this S1, same as this S2S. So yeah, let's go ahead and look. Let's go ahead and verify what state we're in. So if I look in table A3 and I look at, oh, it's not even on here, which is slightly annoying, but yeah, but it'd be between 10 and 15. So our entropy is 6.88. And you can tell, even if I interpolated, that's my S of G value. Even if I interpolated, you can tell that with an entropy of 6.88, it's above that. So clearly we're in that superheated region. So if I go to my superheated tables at 12 bar, 100, definitely not what I need. Oh no. Oh no. Unfortunate, unfortunate, but a good learning opportunity, an excellent learning opportunity. So unfortunately, we don't have a box for 12 bar. We don't have that. We have it for 10 bar and for 15 bar, but we don't have it for 12 bar. So what do? So it's coming out. We've got an entropy of, change colors here, 6.8803 at state 2. That's P2. Fine. Okay. So 6.8803. Yeah. Pretty darn close over here, but I'm gonna do a double interpolation anyway. 6 point, and let me kind of put this a little bit closer. So what I'm doing, I'm filling in some blanks. This is a double interpolation, and it's something that I referenced on the video for interpolation, but we really haven't done it because it is kind of time intensive, but it's worth it to at least go through it maybe one, oh my goodness, maybe once or twice. So this is 6.8803. So at 10 bar with an entropy of 6.8803, we would have a corresponding entropy of, this looks okay, 2919. That looks okay. Yep. 2919.71. So we're all good there. Perfect. Now let's go over to 15 bar and fill in the gaps here. So our entropy at state 2, 6.8803. 6.8803. And then our entropy, our corresponding enthalpy, is going to be between those two guys. And I've got 3016.88. 3016.88. Okay. And now I'm going to say, okay, well now at 12 bar, or I'm sorry, say at an entropy S2S, which is equal to 6.8803 kilojoules per kilogram K. I'm going to make my own table. And it's not organized the same way, but that's okay. So I'll have a column for pressure. This is in bar. And then I'll have a column for enthalpy. This is kilojoules per kilogram. Okay. So I'm going to zoom in on this real quick, okay? So over to the left, all that information was at 10 bar. So get this guy. So this is at 10 bar and an entropy of 6.8803. I'd have an enthalpy of 2919.71. At 15 bar and an entropy of 6.8803, I'd have a corresponding enthalpy of 3016.88. I am at 12 bar, and whatever value that I interpolate here is going to be my H2S, and that H2S ends up being 2958.6. Okay, so if you want a little refresher on double interpolation, it's way back in Unit 1, but there you go. I typically don't like to put double interpolations on tests, but it's not outside of the realm of possibility. It is something that you should know and be able to do. So 2958.6. So 25.6 per gram. And hopefully there is no double interpolation at for one for point is it 0.2 megapascals? Yeah, and it might be. I don't see. We'll see. See. Maybe not. Yeah. Let's go to state 2. So or state 3, I'm sorry. So H3, or I should say H3S. Let's look at the properties there. So our properties, we've got a pressure P3 of 0.2 megapascals, 2 megapascals, which is 2 bar. Actually, I'm sorry, this should, if I look at, I think I've got a typo here because it says it leaves it at 20 kilopascals. So that would really be 0.02 megapascals. Fix that. So 20 kilopascals, wouldn't that be 0.2 bar? So over here is also 0.2 bar. Sorry about that. That was a typo on my part. So delete. So 0.2 bar. And then as our working fluid goes from state 2 to state 3, it's clearly isentropic. So from state 2s to 3s, it's the same entropy. And of course, this is still S1. So let's go look at our tables at 0.2 bar and see what we've got. Oops. Right, and get away from this double interpolation mess. That would be nice, wouldn't it? So table A3. So we are at 0.2 bar. Good, thank goodness. At least we got a line for this one. All right, so our entropy at state 3s is 6.8803, and that's clearly between the S sub F and the S sub G values. So I do know that it's saturated. It's two-phase. So this is going to be S sub F plus my quality times S sub G minus S sub F. So my S, oh, I'm sorry, this is not S. Sorry, guys, I'm recording this at about 6:45 Wednesday. Tired. All right, so H sub F is 251. Sure. Yeah, there we go. 251.4. There's my H sub FG. Okay. So 251.4 plus quality times 2358. All of this is going to be in kilojoules per kilogram. I do need to get the quality here, and the way that I'm going to do that is my entropy, because I know, and this is the quality, the end of that isentropic process. And I know that the entropy is also defined according to that. That's S sub F plus my quality times S sub G minus S sub F. So my quality is going to be S3S, which is 6.8803 minus our S sub F, which is, let's go look, 0.8320. There's our S sub G. So 0.820 over 7, I should put a 0 there, 7.9085 minus 0.832. And I get a quality of 0.85 and change. And so if I plug that in, I've got a H value, H3S of 2267.04 kilojoules per. All right. And so finally, I'm ready to plug in some numbers. And you might panic now because you realize we've only done case A, but don't worry, it won't be so bad. Plug in the numbers. I've got, for this guy, I end up getting 16,290 kilowatts. So I will go ahead and box that. And like I said, you may panic because we got a whole nother case here. But case B is the same turbine, it's just with an isentropic efficiency of 88%. And so since I've kind of already done the hard work, right? So isentropic efficiency of this guy, it relates the two work outputs. And I could put this in terms of W dot as well if I wanted to, right? It doesn't matter. So ideally, I'd get a lot of work out of this guy, so that's going to be the denominator. And I've actually already calculated that because this is the work for the isentropic process, right? Part A is the work for the isentropic process. And so this just ends up being, it's 88%, this would be 0.88 times that 16,290 kilowatts. And that's going to get me, let's see, 14,335 kilowatts. Okay. There we go. Box that. And that puts us close to about 45 minutes. And so I think that's probably where we're going to stop now. And then we'll pick up Wednesday when we come back. We'll pick up on problem 12. Okay. All right. Thanks for watching.